Welcome to section 1.1, semigroups, monoids, and groups. So what we'll do in this section and largely in this chapter is review some of the topics you saw in your senior level Introduction to Modern Algebra class. Of course, this is a graduate class, so we'll have a bit more formality for one, and we'll consider things in a bit more detail as well. So we're going to introduce, in addition to groups, two other algebraic structures, which are weaker than groups. They include all groups, and they include some other structures as well. For background material, I'd recommend John B. Fraley's first course in abstract algebra. At this stage, the 7th edition is the most recent edition. Came out in 2003. I'm talking to you from 2020. And I've got some notes posted on that book, some extensive notes posted on the Fraley book. Excellent background material for this course. Okay, first we need the idea of a binary operation. Let G be a non-empty set, then a binary operation on G is a function from the Cartesian product of G with itself, so ordered pairs of elements of G, into set G. If we denote the binary operation with an asterisk, then we'll use the notation A asterisk B, a binary operation, B equals C. If A and B are the elements of the Cartesian product of G with itself, which is mapped under the binary operation to this element C of G. So strictly speaking, binary operations are functions from Cartesian products into sets themselves. Of course, we'll gloss over that and use more along these lines, more of the highlighted equations in representing binary operations in general. Notationally, we'll consider quote unquote additive and multiplicative binary operations. Unless we have a specific example, it really doesn't matter which of these notations we use, but there's really no difference in these binary operations other than the fact that we'll represent some of them with addition signs and some of them with multiplication notation. But there's really no difference in these binary operations. It's just when we look at specific examples, we'll take preference of one over the other. If we're considering an additive binary operation, then we'll denote the ordered pair AB as A plus B, this ordered pair in the Cartesian product of the set G with itself. If we're considering multiplicative notation, then we'll associate this ordered pair with the product. Rarely will we put a multiplication sign in between them. It's understood that there's a binary operation there, a multiplicative binary operation. In fact, throughout this first chapter, we'll stick with a multiplicative notation, which is not entirely true. Some of the examples we'll see will be additive examples, and some of the exercises in the book will involve additive examples, in which case we'll slip over into the additive notation. But largely the material in the section is written up in terms of multiplicative notation, as we're using in definition 1.1.1. For multiplicative binary operation on the Cartesian product of G with itself, define the following properties. The binary operation is associative if, and let me read this verbally as if it were a multiplicative binary operation, A times the product of B and C equals the product of A and B times C for all elements in this set G. Element E in the set G is a two-sided identity. If A times E equals E times A equals A for all A in this set G. Element A has a two-sided inverse. If for some element of the set, I'll go ahead and read it, A inverse, because that's what we'll call it. We have A times A inverse equals A inverse times A equals E, where E is the identity defined in the previous part. So properties you're totally familiar with from your previous group experience. we're going to look at three structures. A semigroup is a non-empty set G with an associative binary operation. So binary operation satisfying only necessarily the first property. A monoid is a semigroup with an identity. So a monoid, being a semigroup, has associativity and by definition contains an identity. So a monoid satisfies necessarily just the first two properties. A group is a monoid such that for any A and G, that A has an inverse. So a group is a set with a binary operation on it, which is associative. There exists an identity and every element has an inverse. So this is probably somewhat new to you, this idea of semigroups and monoids. You're familiar with your previous experience with what a group is. We'll look at plenty more examples. We'll see a few examples of semigroups and monoids, but just to draw some distinction between these, you're familiar with monoids from linear algebra. When you consider n by n matrices under multiplication, say the entries are real, so square matrices, all of the same dimensions, form a monoid under multiplication. There's an identity because there's an n by n identity matrix. Not necessarily inverses though, because there's plenty of non-invertible square matrices, all the singular matrices. So n by n matrices with real entries form a monoid. Don't form a group because you don't have inverses for some of the elements of that collection of matrices. In a semigroup, and they're defining this in a semigroup, and groups and monoids are both kinds of semigroups with additional properties. So this applies to all of these structures. Semigroup G is abelian or commutative if A times B equals B times A for all A and B. So we've got commutativity with respect to the binary operation. That is, we'll probably more often use the term abelian. That is an abelian semigroup, an abelian monoid, or an abelian group. Little notational observation. Hungerford doesn't capitalize abelian. Arguably he should because it's named after Abel. But we'll follow the notation in the book and use abelian as an adjective and not capitalize it. The order of these structures, be it semigroup, monoid, or group, is the cardinality of set G. Usual notation for the cardinality of a set. If the cardinality of G is finite, it's less than infinity, then the semigroup, monoid, or group is said to be a finite semigroup, monoid, or group. We're here to consider finite groups and infinite groups. Oh, and in passing, semigroups and monoids. After section 1, I don't think we'll see a whole lot of semigroups and monoids. This is largely a class about groups. So the monoid and semigroup stuff is short-lived. We might go a little bit further and define a binary algebraic structure simply as a set with a binary operation on it. And then we'd have sort of this little schematic inclusions of all these little algebraic structures. A binary algebraic structure includes all semigroups. The difference is the semigroups that required associativity. Semigroups, in turn, contain monoids, required associativity, and mono reminds you of one, had an identity. And in turn, monoids included groups. Groups had identities, groups had associativity, and groups had, for each given element, an inverse element. So we get these 4 algebraic structures, if you like. Our concentration really is on groups. Okay, first result, really about groups, fairly straightforward arguments to establish these. We won't go through a proof of this. First states if G is a monoid, meaning it's a binary algebraic structure where the binary operation is associative, that's the semigroup part, and there exists an identity, that's the monoid part. Claim is monoids, the identity element is unique. So there's not more than one identity in a monoid. Of course, this holds for groups as well because groups are examples of monoids. For the remainder of the discussion, we need inverses. And so for the remainder of the statement of this theorem, G is taken to be a group. So if G is a group, then we also have these properties. If C is in the group and C times C equals C, then C equals the identity. How would one prove that? Informally, multiply both sides by C inverse. In a group, you know this element C will have an inverse, speaking in multiplicative notation here. So multiply both sides by C inverse. That'll produce the identity on the right. On the left, it'll give us C times C inverse. The C inverse would give the identity. This would reduce to C equals identity then. So these are accomplished in really elementary ways using inverses. Part 2 claims, for all A and B, if AB equals AC, A times B equals A times C, then B equals C. So we're effectively canceling the A's. They're both on the left. In fact, this property is called left cancellation. If B times A equals C times A, we can effectively cancel the A's since they're both on the right to conclude that B equals C. That's called right cancellation. How do you prove this? Well, on this one, multiply both sides on the left by A inverse. Simplify, it'll produce this. For this one, multiply both sides on the right by A inverse. It simplifies to produce this. So as I said, proofs are straightforward. For any element of A in this group, the inverse element, A inverse, is unique. How do you prove that? Usual argument, assume it's not. Assume we have two identities in each other, two inverses in each other equal. Usual uniqueness argument. For any element of the group, okay, let's read this carefully. This would be the inverse, there you go, the inverse of the inverse of A is A itself. How would you establish that? Multiply these two things together and show you get the identity. So that's how you establish that things are, you'd translate this into an inverse statement and then multiply by A to get the identity out. And that would establish the appropriate inverse. Try to highlight that outermost inverse symbol. But straightforward, and you probably did this in senior level algebra. For all A and B in the group, we have that the inverse of A times B is B inverse times A inverse. This you're maybe familiar with dealing with matrices. When you deal with invertible matrices, this is a property you see. We don't have commutativity. If we had commutativity, this would look more like your familiar experience with real numbers. But without commutativity, we're stuck with drawing this conclusion. How would you establish this? Multiply AB by this thing here and show that you get the identity, establishing that AB is the inverse of this. And lastly, for all A and B, the equations AX equal B and YA equals B have unique solutions in G. So you want to interpret this as A and B are some group elements. Having a solution would mean there exists a group element X such that A times X equals B. Think of X and Y as unknowns. So these are one equation and one unknown. Claim is these have unique solutions when we're dealing with group elements. And in fact, you can find using multiplicative inverses, you can find those solutions. The uniqueness claim is a little something extra though, but certainly we would get these as solutions. Uniqueness we'd show probably in the usual way. So there's some properties of groups. We can somewhat weaken what we've dealt with so far, this idea of a two-sided identity and an inverse that works on both sides. Let's go back to definition 1.1. For an identity, E, we required that we could multiply on the left or the right, and that would produce element A. For inverses, we required that we could multiply on the right or the left with this A inverse element, and that produces the identity. So there was this emphasis on two things, left and right, two-sided, inverse, two-sided, identity. Well, it turns out that if we simply assume right inverses and right identities, then you can show that you have identities and inverses. Or if you only assume left inverses and left identities, then you can show that you have two-sided inverses and two-sided identities. This is a theorem we're about to claim. This is also an exercise in chapter 4 of the Fraley book. So more specifically, if G is a semigroup, G is a group if and only if the following conditions hold. There exists an element E in G such that E times A equals A. For all A, E is called a left identity of G. So there's no multiplication on the right required here. And for each A in G, there exists an element A inverse of G such that A inverse times A equals the identity. And notice there's no requirement that A times A inverse, this commuted, also equals the identity. So we're saying if we have a group, then we have this left identity property. The second one's called a left inverse property for element A. So if we have a group, of course, we've got left identities and left inverses. We've got two-sided identities and two-sided inverses. It's going in the other direction that this is useful, and we'll use this here shortly. If we could show the existence of a left identity and a left inverse, that's sufficient to conclude that we have a group. It's an if and only if result. So we don't have to, given a semigroup, we don't have to establish two-sided identities and two-sided inverses. We can establish only left identities and left inverses, and that's sufficient. Or we could establish only right identities and only right inverses, and that's also sufficient. All right, here's another if and only if result in which we start with a semigroup and give a condition that guarantees that we have a group. Claim is, let G be a semigroup. Then G is a group if and only if for all A and B, the equations AX equal B and YA equal B have solutions in G. Again, think of the X and the Y as unknowns. Okay, we had stated before in a group, we know this kind of behavior holds. This time we're saying if this kind of behavior holds in a semigroup, then we in fact have a group. So let's look at a proof of that, going to the supplemental notes. Okay. All right, first suppose G is a group. Then I could quote one of those previous results, but let's actually just go through and compute it. AX equals B, apply the binary operation with A inverse multiplied on both sides of that equation on the left. So AX equals B implies A inverse, AX equals A inverse B. Associativity allows us to associate this A inverse and A as given here by the very definition of A inverse. Then A inverse A is the identity. So this becomes an identity times X. Right-hand side remains A inverse B. I don't really know anything about those elements. Identity times X is simply X itself, definition of the identity. And we have the solution X equals A inverse B. Similarly, if we have YA equals B, we can solve for Y by multiplying by A inverse on the right, producing Y equals BA inverse. So these do have solutions. Now, of course, if G is a group, then these have solutions because G has inverses is what's making it work. Now, more useful, let's go in the other direction. Suppose AX equals B and YA equals B have solutions. Now we want to show G is a group. We're working under the assumption that G is nothing other than a semigroup. Proposition 1.1.3 says we only need to deal with left identities and left inverses. So we're going to show the existence of left identity and left inverse. From that, it will follow that the semigroup must in fact be a group. So this is where proposition 1.1.3 is useful. Okay, so we're assuming for all A, YA equals A has a solution. Okay, that's this equation. Remember, A and B could be anything, including B could be A itself, as far as that goes. So we're considering YA equals A. We know this has a solution. That's the hypothesis. Let's call that solution E sub A. So that we have E sub A times A equals A. All right, so I choose the symbols E sub A because this is acting as at least a left identity for element A. That doesn't mean it's a left identity for everything. So let's show it is a left identity for everything. Doesn't mean it immediately. Take any B in the group. The equation AX equals B has a solution. Say A times C equals B. So let C be a solution to that equation. Now let's consider E sub A times B. Well, we just said B is of the form A times C. All right, associativity allows us to associate the E sub A and the A. Hey, I know what E sub A times A is. That was a solution to this equation. That's A itself. Remember, E sub A was a left identity for element A. So this produces A, and we get A times C, but we said A times C equals B. So we're getting E sub A times B equals B. Hey, that E sub A that was a left identity for element A is a left identity for everything. B was an arbitrary element. We multiplied on the left by this E sub A thing, and we got B back out. That's what a left identity is. Actually, let's change the notation a little bit, and let's denote E sub A is simply E, since it's a left identity for all elements. Okay, so we got the left identity stuff. Now we need the left inverse stuff. So we'll just consider the appropriate type of equation. Consider the equation YA equals E, where E is this element we've produced from the previous argument. This has a solution, hypotheses. This is a equation of the form YA equals B. We just happen to choose B to be that element E, the left identity. But this has a solution. We're working under those hypotheses in this second paragraph. So that solution then would be a left inverse of element A. You take A, multiply it on the left by a solution to this equation, and you get the identity. A is an arbitrary element. Every element has a left inverse. There exists a left identity, this E element. We got left identities. We got left inverses. We got ourselves a group. Theorem 1.1.3 says semigroups with left identities and left inverses are in fact groups. So there's a little inspiration as to why you would want to use proposition 1.1.3. We only have to check things on the left. If both inverses and identities work, then in the semigroup setting, we got a group. Back to the notes. Some examples. The integers, the rationals, the reals, the complex numbers, all of these form infinite abelian groups under addition. Okay, I warned you we'd see addition pop up as the binary operation in some of the examples. Yeah, no problem with addition. Any element of these structures, the additive inverse of those elements are there. 0 is the additive identity. It's in all 4 of those structures. Oh, and addition is commutative on all of these structures. So infinite, because there's so many numbers, abelian from the commutativity, and inverses and identities. Everything's covered with that with respect to addition. Each is an abelian monoid under multiplication. Okay. Multiplication is definitely a binary operation. Multiply 2 of these numbers together and get another in that respective set. Product of 2 real numbers is a real number, for example. Product of 2 complex numbers is a complex number. Could also be a real number as far as that goes, but that's encompassed by the complex numbers. Monoid, we need then an identity. Under multiplication, 1 is the identity under multiplication, and each of these include the number 1. Not a group, because 0 doesn't have a multiplicative inverse. So there's an example of, several examples of an abelian monoid that's not a group. We spoke earlier of square matrices. Here's a specific collection of matrices. Consider the set of all 2 by 2 matrices with real entries. This forms a non-abelian monoid. Okay, under matrix multiplication. It's not a group because 2 by 2 matrices can be non-invertible. So under multiplication, no inverses for some of these. So I'm not a group. Identity, you got the 2 by 2 identity. Non-abelian, right, matrix multiplication isn't in general commutative. So here's another example related to monoids that aren't groups. We can take the non-zero elements of the rationals, the reals, and the complex numbers and form an infinite abelian group under multiplication. In fact, we'll see some of these manipulations deeper in the course. So what we're doing is simply removing 0 from these 3 sets and saying under multiplication, now you got yourself an abelian group under multiplication. What are you worried about? Well, multiplication is associative, no problems with that on these collections of numbers. Identity, yeah, all 3 of these contain 1. They don't contain 0. Good thing they don't contain 0, because 0 doesn't have a multiplicative inverse. But all these other numbers do have multiplicative inverses in the relevant structures. So by throwing out 0, by the way, another idea of 0 is it's the additive identity, arguably beyond the scope of this first course, to have 2 binary operations, but you're familiar with this probably from your past. If I have 2 binary operations, I usually denote one as addition and the other one as multiplication. Not the realm of group theory, though, the realm of ring theory. But it's common to throw out an additive identity from a ring and take what remains and create from it a multiplicative group. The even integers. So take the integers, throw out all the odd ones, forms an abelian semigroup under multiplication. All right, a product of 2 even integers is an even integer, so we're good on that. Semigroup, but not a monoid, and so not a group. No inverses. Yeah, 2 is an even integer, and it doesn't have an inverse that's an even integer. So, in fact, there's no inverses for any of the even integers. Identity under multiplication, I need 1 for that, and 1's not an even integer. So that's why we don't have a multiplicative identity, and that's why that collection of numbers forms a semigroup, but not a monoid. No multiplicative identity, 1 isn't in this collection. Okay, here's something you've encountered no doubt in the past. I'm going to go at it a little differently in this first section. We'll explore dihedral groups later in more detail and give a clean definition of them, just kind of playing with the concept of a group at this stage. Hungerford describes a group D sub 4 star of transformations of a square, it's the group of symmetries of the square, by considering this picture. So here we got a square. It's effectively labeling the corners 1, 2, 3, and 4. Is given. He's introduced an x-axis and a y-axis, and we're going to have as group elements manipulations of that square, not the square itself, not the 1, 2, 3, and 4, manipulations of that square as it lies in that xy plane, in that Cartesian plane. We're going to consider the transformations, these 8 things here. I, the identity transformation that simply leaves that square where it is. R denotes a counterclockwise rotation through 90 degrees. So if we apply R to this square, it'll rotate it counterclockwise 90 degrees. So the 1 will rotate around to the 4 will rotate over to the 3 will rotate up to the 2, and the 2 will rotate over to the 1. R squared, apply that twice. It'd be a counterclockwise rotation through 180 degrees. R cubed would be a counterclockwise rotation through 270 degrees. So then the 1 would be mapped to the 2, right? It'd go around 90, 180, 270, and so forth. T sub x is defined as a reflection about the x-axis. So T sub x would take the square, map the 1, 2 down here to the 4, 3, respectively. Just flip it over. T sub y similarly is a reflection about the y-axis, so it would map the 1, 4 edge to the 2, 3 edge, respectively. And a couple of other reflections, T sub 1, 3 and T sub 2, 4. T sub 1, 3 is a reflection about the line through the points labeled 1 and 3. So we've got an axis of symmetry of the square that would go through this point, through the origin, and through that point. Applying a reflection about that line would leave 1 and 3, these corners, fixed, and would interchange the 2 and the 4. So it's also a flipping around of the thing, a reflection of the square about a certain axis. And we could similarly have an axis that runs through the points 2 and 4 as labeled in the origin, which would leave 2 and 4 corners fixed and interchange the 1 and 3 corners. So there's 8 transformations of that square, 8 symmetries of that square. And in fact, we could define a binary operation. The binary operation on these transformations is, it's really function composition. So we'll compose these transformations as functions on the numbers 1 through 4. So the behavior of these transformations on 1, 2, 3, and 4, those corners, determines the behavior on the square. For example, if U and V are transformations, we'll denote the composition of those 2 transformations, U star V. So we're using function composition as the binary operation. This ain't the last time we'll use function composition as the binary operation in a group. Function composition is associative, something you encounter in senior level algebra. So we've got the associativity already. We have an identity, the identity transformation that didn't change anything. It left all the 1 through 4s fixed. And I bet you we have inverses. In fact, some of these elements you can geometrically see are their own inverses. We consider T sub x. So take the square, reflect it about the x-axis. So the 1, 2 comes down to the 4, 3, and the 4, 3 goes up to the 1, 2. How would you undo that? Reflect it again. So T sub x is actually its own inverse. T sub y is its own inverse. T sub 1, 3, T sub 2, 3, these are their own inverses as well. Specifically, here's a composition of 2 of the transformations. And you can see by following the way the corners are mapped around, you can pick out that our binary operation T sub x is equivalent to T sub 2, 4. I bet you this is not an abelian group. An exercise 1.1.4 in the book as you go through and confirm, quite tedious in fact, not terribly enlightening either, but here's what you get if you'll take those 8 operations, multiply them together. We're taking the 1 along this column times the 1 along the top. So order of multiplication matters. This is not abelian, as can be seen by maybe taking r cubed times T sub x and getting T sub 1, 3. And taking T sub x times r cubed and getting, well, I guess we do also look at T sub 1, 3 there. Bad choice. I should maybe look at this entry and this entry. These are in corresponding positions, but they're not equal. So we don't have an abelian group with this dihedral group. So there's what we get for that group. We will generalize that. So I'll start a new presentation shortly, and we'll go through and put this in a more general setting of permutation groups. And that's probably where you've encountered symmetry groups before versus groups of symmetry. So have a nice day. I'll get to working on the remainder of this section and get that up and running for you shortly. Bye-bye.